Hello, fellow problem solvers. So today we're going to be solving problem 5 from the 2025 IMO. I suggest you try this beautiful, problem out for a minimum of 45 minutes, ideally 90 minutes to 2 hours, not more than 4.5 hours. If you'd like to go along with us, give this a go for the next 10 minutes. So read the problem, put your first ideas out on paper. Now let's begin. So when you read this problem, what do you see? Well, you see a bunch of things. Wow, like what's happening here? What is lambda? And there's a game. So, okay, let's put things down on paper first. So, actually, let's just go right into solving it. So, how do we solve a problem like this? How do we even understand a problem like this? What's a principle that I put in a lot of videos? I put in the video for my advice for the 2025 IMO. Hope you watched it. 2 pieces of advice. Simple ideas before complex ones, and play around small cases. This is beautiful for small cases. So let's see. We have, okay, let's write this down. We have these sums, x1 plus all the way till xn needs to be less than or equal to lambda n, and the sum of the squares, xn squared, needs to be less than or equal to n after the second player plays. Great, sure, phenomenal. So let's see what happens. So the first one, x1 needs to be less than or equal to lambda. Okay, and then we'd have that x1 squared plus x2 squared needs to be less than or equal to 2. Okay, so first question. How could the game end immediately on move 2? Simple idea, just like what could happen. Pause for 5 minutes, figure it out. And the answer is, well, say if lambda was big enough that we put it x1 equals to lambda, the biggest one, sort of greedily thinking about this, we'd have now lambda squared plus x2 squared needs to be less than or equals 2. But if lambda was greater than the square root of 2, then this would be strictly greater than 2 plus x2 squared. In other words, we'd have that the second player needs to give an integer, a real number x2, such that its square is less than 0. Impossible. Ergo, player 1 wins. So for lambda greater than 2, player 1's a winner. Okay, cool. Now, let's maybe see, okay, could the game end? So player 2 would need to make a move for the game to end for player 1, regardless of what lambda is. But let's say, like, could it happen that player 2 wins? Like, immediately, like, after making their move, that basically player 1 can't win such that this is less than or equal to free lambda. So how could that happen? Go ahead, pause, and figure it out. So, I mean, if you think about it even in these terms, so player 1 is concerned about this lambda times n. And if this is pretty small, in comparison to n, player 2, like, yes, it's a square, but these are going to be, say, small numbers. So, like, the number itself is going to be bigger than the square. Player 2 is going to win. So, what's the thing to do? So, let's say, okay, when does player 3 win? Well, if this thing is strictly greater than free lambda, then they win. In other words, why do we win here? This thing was greater than 2. So we need this thing to be strictly greater than free lambda to win. Okay, so after player 1 puts in an a that's less than or equal to lambda, greater than or equal to 0, what should player 2 put? Well, they should put the biggest thing they can put, which is 2 minus a squared, and square root that. They should put that, the biggest thing. Now the question is, a plus the square root of 2 minus a squared. We need to make this bigger than free lambda. So how can we make this bigger than free lambda? Well, we need to, first and foremost, like, find a lower bound on this. Okay, how do we do this? Well, let's think about this. We have x plus y is a constant, c, right? X plus y is a constant, and we need to, actually no, x squared plus y squared is a constant. We need to find the lower bound of x plus y. Okay, X plus Y, well, so this is just generally algebra. If it's not when they're equal, then it might be on the extremes. So when x is the square root of c. So let's try to prove that this is greater than or equal to the square root of c. Okay, square it. We get this is then x squared plus y squared plus 2xy is greater than or equal to x squared plus y squared. Okay, we've proved that this is greater than or equal to c. Cool. Or, I mean, another way to just say this is we've shown that x plus y is greater than or equal to the square root of x squared plus y squared. And that's pretty much it. So now this is greater than or equal to the square root of the sum of these squares, which is the square root of 2. So if the square root of 2, the square root of 2 again. Okay, if the square root of 2 is now greater than 3 lambda, player 2 wins on move 3. So if we have square root of 2 divided by 3 less than lambda, okay, this is a win for player 2. Okay, cool. So we're starting to get a feel for the problem. Do you have any idea what to do next? No? Pause for 5 minutes. And what should you do when you pause for the next 5 minutes? If you have no clue what you want to do, you should play. And let's do that. Let's continue on with 4. So under which circumstances? So now we know, okay, for lambda greater than the square root of 2, player 1 wins. For lambda less than the square root of 2 times 1 over 3, player 2 wins. Let's say that the game actually went on. So x1 was less than or equal to lambda. x1 squared plus x2 squared was less than or equal to 2. And then x1 plus x2 plus x3 was in fact less than or equal to 3 lambda. And then we want to see how can player 2 lose now. So for them to lose, we need the sum of these three numbers, to somehow, so this needs to be less than or equal to 4. So we need to somehow make sure that these three numbers sum up to something that's greater than 4. Okay, well, let's see. We would need to, ergo, we would have, say, x1 plus x2 plus x3. Well, if we set it equal to 3 lambda, then we're trying to find the minima, so to speak, of this. Though this is greater than or equal to the sum of these, x1 plus x2 plus x3, divided by all of this squared, divided by 3, by the Cauchy. So then this is then going to equal 9 lambda squared over 3, so 3 lambda squared. So now, if 3 lambda squared, if this thing right here is greater than 4, in other words, if lambda squared is greater than 4 thirds, then player 1 can win. Assuming everything goes well here. Fair enough. Let's play more with this idea. We're still really not done with 4, but let's just explore like what the bounds, how the bounds may move. Because you want to push down player 1's lambda and push up player's 2 lambda. So player 2 now plays and say this is actually good. But player 1 cannot play, which means what? It means that the sum of these 4 numbers, in fact, is greater than 5 lambda. Now, what do we know about these 4 numbers? Can we estimate anything off the bat like this? We can say, okay, let's say that the sum of their squares, x3 squared plus x4 squared, let's say this is 4. And in fact, what if player 2 just maximized? Then I think this is very hard for us to estimate, and we'd have a lot of terms on the sides, even terms we don't control. What if we instead estimated this? Because like the way we can estimate this now is to say, okay, this thing right here is greater than, so what do we do here? We said, okay, this is now equal to, has to equal, what did we put down? Here is what we had, this estimate. This needs to be greater than 3 lambda. And we had an estimate of a and 2 minus a squared. What if just at each turn, we actually just estimate that? Would that be stronger? I mean, it definitely would be. It seems like it could be stronger, potentially. So let's actually see what happens here. Because now you want to estimate this in some way, shape, or form. So to sum the squares of these numbers, well, the only thing we can really say is that this number is greater than the sum of the square roots. And here the sum of the square roots, the square root of all of this, is 2. And that is it. That is all we can say. So if 2 is greater than 5 lambda, then we win. In other words, lambda, actually, no. If 2 is less than 5 lambda, we should be able to win. But this thing actually doesn't seem to be working that well. No, actually, this is player 2 winning. So as long as this is the case, as long as lambda is less than 2 over 5, we're good. But 2 over 5 as an estimate is actually not as good as the square root of 2 over 3. So we got a worse estimate. So we can't do just this. And this is weaker because we're leaving out a bunch of terms. What if instead, just equalize this, and we said x3 squared plus x4 squared was also equal to 2. What estimate will we have then? So we'd have the square root of 2 plus the square root of 2. Now this thing would need to be greater than 5 lambda for us to succeed. Or just lambda would need to be less than 2 over 5 square roots of 2. Okay, now this is actually a better estimate because this is greater than 1/3 of square roots of 2. And we want better and better estimates. So this is actually good for us. Now the question is, for you, what should you do next? I'm going to clear this up and give you now a bit of a overview. So we found that some lambda for player 1, and we were now playing around with small numbers. Now let's look at some simple ideas. A simple idea would be to be greedy, maximize at each turn. So this would be player 1, whenever they play, they first play to make it lambda, then player 2 plays an a, they play 2 lambda minus a. They play b, they play 2 lambda minus b. Always to maximize their own sum. And that would lead to a situation where the second player, they're able to play as long as all of this, the sum of all of these a's, is, so let's actually write this down. Instead of a, they played x1, x1, actually x2, x2, x4, x4. So when the second player played, it was lambda squared plus x2 squared plus 2 lambda minus x2 squared plus all the way till x2k squared plus 2 lambda minus x2k squared. So for them to be able to make a move, they're making the even move, this thing needs to be less than or equal to 2k. Okay, we get a contradiction if it's greater than or equal to 2k. So what is this thing greater than or equal to? Well, it's lambda squared plus, how do we estimate these two? Well, it's at least 2 lambda squared plus 2 lambda squared plus 2 lambda squared. You can estimate all of these with 2 lambda squared. You have how many of these? From 2 to 2k, you have k of these. So you get 2k 2k plus 1 lambda squared. So if we can always do this as player 1, this is, assuming like we're always maximizing, and for us to maximize, the only thing we really need is 2 lambda minus x. We need this to be greater than 0. So whatever xi they play, we just need to make sure that it's less than 2 lambda, and we're good. Now, there's this very simple reason why it's less than 2 lambda. Actually, it's not super simple. We would still need to just prove it. But basically now, so they'll be able to play as long as this is the case. Now, in which instance, so 2k would need to be greater than or equal to this. In which instance is this going to be greater than 2k? Well, if lambda squared is less than 1 plus 1 over 2k plus 1. So as long as, pause for a minute, figure it out, as long as lambda is greater than 1, player 1 can win by being greedy, by always trying to go to the top. Take the max, take the max, take the max. So this means if player 1 is always taking the max, so if lambda is greater than 1, player 1 always takes the max, and what will they do? They'll take lambda, which is greater than 1, and then player 2 plays. Now what's cool about player 2? Because player 1 has a number that's greater than 1, player 2, if they play x2 squared plus lambda squared, this is less than or equal to 2. If this is less than 1, if this is greater than 1, that means x2 is less than 1. And then inductively, what you'll have then is lambda squared plus 2 lambda minus x2 squared plus x2 squared, plus now you need to put in x4. Well, this number is less than 1, greater than 1. What about this number? It's greater than 1. For them to be less than or equal to 4, this needs to be less than 1. And so, like, you see, like, what's happening is we're always going to be playing a number that is greater than 1. We're going to be playing a number less than 1. And ergo, we will always be able to play this, right? Because 2 lambda is greater than 2. This is less than 1, which means this whole thing is always going to be actually greater than 1, in fact. And then the other one is going to be less than 1. Amazing. So their x is always going to be less than 1. We prove this inductively. And so we are done, as the first player, playing greedily. Simplest strategy. And we win. Now, what other simple strategy can we test out? Well, what if player 2 is always greedy? And from that is just say that player 2, if we play a, they play 2 minus a squared, square root that at each time. And what do they get? So they can play as long as whatever we play is less than the square root of 2. So, okay, we can assume we're looking at, okay, lambdas now. We're looking at a lambda that's less than 1. So initially this is good. Let's assume it's, we can first make sure they can play it, or we can look at what this will actually entail. Let's look at what this will entail. We have played x1, they've played the square root of 2 minus x1 squared. And then we played x2k plus 1, x2k minus 1, and they played x2 minus x2k minus 1. And now it's the turn of player 1. Now player 1 can play if this is at most, not at least, at most, if this thing is at most 2k, so we play on odds, so it's going to be 2k plus 1 times lambda. We need a contradiction. So we need to say what this is greater than or equal to. Well, we've shown previously, as long as a is less than the square root of 2, this is less than the square root of 2, plus the square root of 2, plus the square root of 2, how many times? From 1 to 2k minus 1, that is k times the square root of 2. Okay, so under which conditions will k times the square root of 2 be greater than 2k plus 1 lambda? Pause for a minute, figure it out. Well, the way I like to think about this is Okay, this means that k, get it out, square root of 2 minus 2 lambda needs to be greater than lambda. If we get this for some k, it's a contradiction. I mean, then we get a contradiction. That means player 1 cannot play. Under which conditions can we get this? This is a constant. This is a variable. So as long as this is positive, we can get it. So as long as the square root of 2 divided by 2 lambda, as long as this is greater than lambda, we can get it. So if this is the case, player 2 should win as long as the strategy works, as long as they can always max and be good. Now let's actually test that they can max and be good. So we would prove this inductively. So initially, if this is the case for lambda, initially this is correct. Now, let's say we've done a bunch of these plays. This one squared, yada, 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 all the way till x again, 2k minus 1, plus the square root of 2 minus x, 2k minus 1, squared. And now they need to play their x. And when they play their x, the sum is less than or equal to 2k plus 1 times lambda. We've assumed this, so we can just plug it in. And this is going to equal k square roots of 2, going to be strictly less than, actually, k square roots of 2 plus square root of 2 over 2. On the other hand, each one of these is greater than or equal to square root of 2, so we're going to have k square roots of 2 plus x. So when you combine these two, you get that x needs to be strictly less than square root of 2 divided by 2. That's the move that they can play. In other words, this is true. So you will always be able to play this in response as the second player and win. So as long as now lambda is less than the square root of 2 divided by 2, player 2 is a winner. So now, what happens between 1 and the square root of 2 divided by 2? Pause for 5 minutes and figure it out. So here, let's look at what we've done. Just like general problem solving, learning from this problem. So from this problem, what we've done is we've seen, okay, simple strategies so far have led us to, if player 2 is just being greedy, lambda less than square root of 2 divided by 2, they win. And they employ a strategy of a and then the square root of 2 minus a squared. That's their strategy. If player 1 is being greedy, lambda is greater than 1, they win. Now the question is, okay, what about for 1? What about these other numbers? Who wins? Or is the game maybe the game goes on infinitely? Or somebody wins. So here, what we were doing here was like 2 lambda minus a and a. Now let's think about this. So for 1, we really have that sum of the xi's, xn squared times n. This is less than or equal to n squared. This is greater than or equal to x1 plus xn squared. So the sum of the xi's is going to be less than or equal to n. Which means, player 1 can't really lose as long as lambda, even if lambda is 1. They can't lose because of this inequality. As long as this is satisfied, they will not be able to lose. For the player 2 to beat them, is what we saw, they need to come up with a situation such that the sum x1 through xn is greater than n plus 1. Right? And then the other player can't make a move. That's what they've done when they were playing greedily. So, actually not n plus 1, but actually n plus 1 times lambda. My bad. But, if lambda is at least 1, then this is at least going to be n plus 1. But if this was greater than n plus 1, we'd get a contradiction on something that's, we know this is always true. Always we know this is true. So lambda goes to player 1. So maybe now there's a way to look at, okay, what other strategies can player 1 do? That they're just maxing at each point. Let's now go back to 2 or free moves. And let's see what happens when they initially don't win. What if they play a 0? The smallest number, like look at extremes, see what's happening, just for an exploration's sake. Then they play a with a squared less than or equal to 2. And then we can play 3 minus a. Actually, 3 minus a, 3 lambda minus a. So now what happens? Well, we win. To win, we need to make sure that this thing, so they'll be able to play, if this is the case, we need to make it greater than or equal to 4. Actually, strictly greater than 4. Which we were not able to do with this greedy approach. But now we can estimate this with the sum of these two variables as greater than or equal to 9 lambda squared divided by 2. And this is greater than 4 as long as, once we square root this, as long as lambda is greater than 2/3 the square root of 2. Pause for 5 minutes, push the problem further. And now how do we finish up? Well, okay, this works. Now we have a better estimate for lambda. Maybe that's what we need. Maybe we need to push it like this. So let's say they do 0, then a squared less than or equal to 2. We do 0, they do b with a squared plus b squared less than or equal to 4. And then we do 5 lambda minus a minus b. Let's estimate this now. This is a plus b plus 5 lambda minus a minus b. All of these squares greater than or equal to what? The sum of these squares squared over 3 is going to be 5 lambda squared over 3, which is 25 lambda squared over 3. And we win if this is strictly greater than 6. If lambda squared is greater than, when we square root, if lambda is greater than 3 over 5, the square root of 2. Now mind you, what we found previously was this thing worked for the square root of 2 times a half, and now we're getting 2/3, 3/5, a lower and lower number. So, what if this is the idea? Let's explore it. Under which conditions can we do this? If we just play zeros, they play x2, 0, x4, x2k. And then we want to just put in everything. What's really happening here? Well, what's really happening is we're sort of creating some space for ourselves. We're sort of letting this thing grow. I think the important part here is that between any two moves, their sum changes by a squared plus b squared. R changes by a plus b. Now the difference between these two is, of course, this is, yes, squared, but we're adding to it and has this divide by 2 component. But this whole, our sum changes by 2 lambda at each turn. So it's changing by the square root of 2, and there's something there. But here, what would be happening is we'd have x2 squared less than or equal to 2, x2 squared plus x4 squared less than or equal to 4. What this is after they make every move, which means not at every single one of these xi's is less than or equal to 2, but they're not going to be huge numbers. And also, mind you, big numbers don't serve player 2, generally speaking. So they're going to have x2 squared plus all the way till x2k squared. And then we play our number, which is going to be what? It's going to be 2k plus 1 times lambda minus the sum of all numbers previously. Then we max it. So now this whole thing, we want to say this plus 2k plus 1 lambda minus the sum of all of these, x2k, and squared all of that. This thing right here needs to be for the second player to be able to make a play less than or equal to 2k plus 2. We need to estimate this. How do we do this? Well, let's see if we can continue doing what we did before. And maybe before doing this in a complex way, let's see if we had a squared plus b squared plus c squared plus, that would be, so 2k plus 1, so it was 5, it would be 7 lambda minus a minus b minus c squared greater than or equal to what? Divide by 4, that's the number of these, so here we would divide by k plus 1, right, so the number of these divided by 2 plus 1. And then here we would have the sum of all of them, which would just be 2k plus 1 times lambda squared. And we would need to have that this is greater than, actually this is 2 times k plus 1. Now if we square root this, this is equivalent to 2k plus 1 times lambda being greater than square root of 2 times k plus 1. In other words, lambda being greater than k plus 1 over 2k plus 1 square roots of 2. So we can win as long as this is the case for some k. And now, of course, we can write this as long as it's the case that lambda is greater than a half plus 1 over 2k plus 1 times 2 here. So we have 2k plus 1, then it's 2k plus 2, plus this, times the square root of 2. And so as long as, so under which condition, so if lambda is this greater than this for some k, then player 1 is able to win. So this means that for any lambda that's greater than a half times the square root of 2, player 1 will be able to win. Given that, of course, the big if is that player 2 isn't able to beat them at their own game here. And the reason they're not is actually simple. So what does it mean that player 2 wins? So this works just as long they can always make a move. And they could always make a move as long as the sum x2 plus all the way till x2k is less than or equal to what? 2k plus 1 times lambda. This is what we need to check. And we can do this, maybe not, we can say this like strong induction as always, we can just use that as a given. But we know that the sum of all of these, x2 squared plus all the way till x2k squared, we know that this is less than or equal to what? It's less than or equal to, we have 2k. By assumption, this is what's constraining them. And then to bring it down towards us, this is less than or equal to the sum of all of the numbers, all of these numbers, x2 plus all the way till x2k divided by k, and this is squared. So in other words, we have that x2 plus all the way till x2k is less than or equal to k times the square root of 2. Now, with that in mind, does this hold? Well, this will hold if this thing is true, so let's say lambda is bigger than 2 over this, like the square root of 2 divided by 2. So then we'll say if this is true for square root of 2 divided by 2, 2k plus 1, it will be good. In other words, if this is true, so this is now, actually, yeah, this is how we finish up. This is now strictly less than k square roots of 2 plus square root of 2 over 2, which is equal to 2k plus 1 times square root of 2 over 2, which we know is strictly less than 2k plus 1 times lambda. So we can always play as the first player following this strategy. And now we've basically shown, okay, player 1 wins if lambda is greater than the square root of 2 over 2. Player 2 wins if it's less than it. Now what happens when lambda is equal to the square root of 2 divided by 2? And this is the final part of the problem. Mind you, what did we figure out? We played around with the problem, moved a couple of pieces here and there, employed very simple strategies. First, let's maximize at each turn. Let's look at small numbers. Let's see what's happening. And then what we said is, okay, wait. Let's now actually do something beyond this. Let's do another simple strategy first. Let's just play a 0. And then we see, wait, we have a better estimate of lambda. And then we say, okay, what if we played 2 zeros? Oh, an even better estimate. So now what we need to do is then, okay, let's try this idea out. And now we get to a point where we've figured everything out except this one point, the square root of 2 divided by 2. So what is true for that? I invite you to take a minute to figure it out. And what we have is, okay, we need to show basically that both players will survive. Nobody wins here. And that is sort of, what makes sense. So let's see if both players follow their optimal strategy. So for player 1, they want to survive. The claim is as long as they play a 0, whatever the other player plays, x2, you play a 0. And you will make it. Now to prove that this is the case, well, if the other player always plays a 0, you just want to prove that after whatever they've made. So they need to satisfy x2 squared plus all the way till x2k squared needs to be less than or equal to 2k, which we saw previously implies that x2 plus x2k is less than or equal to k square roots of 2. And this is good enough for us because what we need to be able to do, we need to be able to play on this. But we will be able to play as long as the sum is less than, and this is in fact, less than 2k plus 1 times the square root of 2 divided by 2, which is 2k plus 1 times lambda. So we're good. As long as we play zeros as player 1, we can win. Now as player 2, we employ the same strategy that we used to win. So if we just play for any a, we play it as the square root of 2 minus a squared. This thing that got us, closest to these bounds. And you see, like, the only sort of addition, this is interesting, is this added constant factor in all of these estimates, which is why I think this problem is just so beautiful, because the estimate is so tight. You can't move it one way or the other. And it's a beautiful game, I must say. So now, to finish up, where we play a, inductively, it would be the same way we would prove that previously the lower bound of the sum, so that they always need to play something less than or equal to the square root of 2 divided by 2. So they need to start off with less than or equal to square root of 2 divided by 2. And then what we have, well, our sum is maximized, and their sum becomes x1 plus the square root of 2 minus x1 squared plus x2k minus 1 plus the square root of 2 minus x2k minus 1 squared. And now the sum of all of these numbers, we estimated that this is now greater than or equal to. So we can play as long as this is less than or equal to let's go, wait a second. Yeah, we're able to make display as long as this actual sum is less than or equal to, actually, no, we can always, actually, no, wait a second. We can always make display. We just need to show that, what's it called? The next player cannot play anything that's greater than the square root of 2. The square root of 2 divided by 2. So here what happens is they need to now play their x, and this thing needs to be less than square root of 2 divided by 2 times how many things we have here, 2k plus 1. But this is greater than or equal to the square root of 2 times k plus x, which implies that x is less than or equal to the square root of 2 divided by 2, which means we will continue to be able to play this and survive. And that's that. That shows that both players can then just like alternate. Neither one of them can necessarily beat the other, and so the game can go on infinitely if lambda is equal to the square root of 2 divided by 2. And this solves our problem. Now, what do I absolutely love about this problem is the fact that you have, like, you're really employing these basic principles of, okay, let me play with it. Let me see what will happen if I put in just a simple greedy strategy. Okay, for player 2, you can do a lot. And it might not be the most intuitive, but you're just trying to see what's happening with the problem to get a sense of the intuition behind it. Because you have these small numbers, there are squares that aren't as big, big numbers, squares are bigger. And then you're trying to then see, okay, wait a second. If I'm able to just maximize each turn, I'm kind of able to like win against the first player if lambda is small enough. And you find the lower bound from lambda. And I think the player 1 strategy is harder because it makes sense to just like be greedy initially. And then you say, wait a second, by just being greedy from the get-go, I get a 1. And then the big question is, okay, can I get a low? I mean, I can barely get a 1. But 1 seems like I have to get it. Can I get something smaller? Like a 0.9, 0.99? And then you see, okay, instead of playing something that's large, I'll play a 0, they play the square root of 2. And then I can play free lambda minus the square root of 2. Wow, what I'm playing is then huge in comparison. Right? Because then what I'm playing plus what they're playing is like the squares of what I'm playing then my square, if it's around 5-ish, I'm kind of winning. Actually, if it's close enough to 4, I can win. And I think then that becomes like the next, not even close to 4, you need to be close to 3. The square of that, if it's close to 3, you win. And then you see, okay, so this is the thing. And if you stop and think about it, then you might be thinking, wait a second, so what I'm really trying to do is create space for myself and then like occupy that space. Because what they can't, like with this lambda that's not small enough for them, they can't cover enough of my territory as much as I can sort of like create space. Because I have an extra move that creates space, they're trying to break space. But I want to create more and more space so that when I get this, the square becomes very large. And I think like that's the very, very cool idea. That basically that's how you solve the problem, and that's and that ends up being the solution. I found the problem to be particularly cool because of that. And it just employs these like basic strategies, these heuristics that come up again and again, and will help you in your problem solving journey. So this was a very, very fun problem to solve. And as always, thanks for problem solving.